Okay, folks, so today we're going to take some basic notes over variables and graphing. Here are the three things that you need to be able to do by the time you are done with today's lecture. You need to be able to identify dependent and independent variables. So if I give you a prompt about an experiment or something like that, you need to be able to tell me which variable is which. You need to be able to draw a graph. You need to be able to read a graph. In my opinion, this lecture won't be the most thrilling because this should all be reviewed for you. So during this lecture, you should be like, yep, remember this. Yep, I got this. So that's kind of what we're going through here today. I'm also going to be using a bunch of the worksheets that are in your Unit 1 packet. So if you haven't gotten that out yet, go ahead and hit pause on your video and grab that. So we're going to start by taking a few notes on controls and variables. Okay, so what is the control variable? So that is the normal. It's not changed. It's not tested. It's used to compare. Okay, so what I mean by this is if you never did the experiment, this is what would happen normally. Okay, so this is like a group usually where you just want to see what would happen if you never did the experiment. What is like the normal? And you use this group to be to compare other things back to it. Okay, so the control group is what you use to compare. It's how you know what change did or did not happen. Okay, now the dependent variable, that is what is being measured or observed. Okay, so this is what you're measuring, this is what you're observing. And it's the variable on the vertical, or known as the y-axis. The y-axis, so that's the one going up and down on the side of a graph. And the independent variable, that is what you are testing. Typically, you pick the independent variable, so that's one that you can pick before the experiment actually begins. You choose what you want the independent variable to be. It is plotted on the horizontal axis, also known as the x-axis. Another way to think of this is, so you pick an independent variable ahead of time before the experiment starts, and then the dependent variable is something that changes because of the independent variable. The dependent variable depends on the independent variable. All right, so let's just go ahead and put this into practice. So here you'll notice I had to make some edits where I put Mr. Pilcher in and his and he because I sent you the one with Miss Bay's name in it still, but whatever. So Mr. Pilcher thinks that drinking Monster Energy drinks will increase the productivity of his students. He takes 2 classes of 30 students and assigns each class the same task. In this case, they're supposed to copy the statement, "Chemistry rocks." Can you imagine if I made you guys do that? Into their notebooks as many times as possible in 1 hour. I forgot how long we made that. Yeah, go ahead and write "Chemistry rocks" as much as you can for an hour. Anyways, Class A is given the Monster to drink while they work. Class B is not given anything to drink. After an hour, Mr. Pilcher counts how many times the class has copied the statement. Group A copied the statement 1,587 times. Group B copied the statement 2,113 times. Okay, so what is our control group? That is a group that is like the normal, where we didn't change anything. They're used to compare. Well, in this case, that's definitely going to be class, or I should say group B, class B, whatever, because they weren't given a monster. So that's what normally happens in class. You don't get a monster when you walk in. So that's our control group. Our independent variable, so what did we pick? What is the thing that we picked before the experiment actually started? Well, that's Monster Energy drink. We decided to give some students Monster and to not give other students Monster. So that is a choice that we made before the experiment actually started. Now, what depends on the Monster Energy drink? What are we measuring? What are we observing? That is the productivity, or in other words, how many statements the students are writing. How many times are they writing "Chemistry rocks"? So I use the word productivity there. There's a lot of answers you could put. But basically, we're observing how often they can write the statement "Chemistry rocks." Okay, should he accept or reject his hypothesis? Why or why not? Well, so the hypothesis was that Monster Energy drinks will increase productivity of students. So students, in other words, will write "Chemistry rocks" more when they're given Monster. Well, we saw in the experiment that Class A, who was given the Monster, wrote "Chemistry rocks" less we're comparing it, they wrote less than chemistry class B, our control group. So compared to the control group, they wrote less times, they were less productive, so we would reject because that less the task was performed by those kids who received Monster. How could this experiment be improved? There are a lot of answers to this question. Some things I thought of were, maybe you could change the task. Okay, writing chemistry rocks over and over again, that's not real like productivity because I would never actually ask you to do that in class. Maybe I should have asked students to do chemistry problems. Maybe get a larger sample size with more students. Okay, so we just had 2 classes. Maybe if we did this with like 1,000 students instead of like 60 students, that would make our results stronger potentially. Because sometimes if you have a very small sample size, you can get results that are kind of skewed or don't represent the larger population. You could work with less or more Monster. Maybe it's like, okay, maybe 3 cans of Monster has a different impact, or maybe, why don't we just give them like a half a can of Monster because a whole can is like overkill. So maybe that would have an effect on the experiment, make it better. What kind of Monster delivery system are we talking about here? We never defined how they should drink Monster. So what if Billy over here just downs a whole Monster in like 2 seconds and he's like on 10 after 5 minutes in the class? And what if Sally drinks the Monster slowly over time? We never really told the students how to drink the Monster, so that could add some variables into the mix that we haven't accounted for. Maybe some other idea. Maybe we should change the groups. Maybe the only reason that class A was less productive was because they're the morning class and they're like kind of walking to class half asleep already. What if we switched and gave class B the Monsters and class A nothing? How would that impact our results? And there's a lot of things you could have said here. You just always want to consider, okay, how can we make this experiment better? What are things that we could change? That should be a question you're always asking yourself. Now, there's some more practice you can do here. This worksheet has plenty of practice. If you felt like you killed it with that last, the Monster experiment, then maybe you do one more practice problem to see if you're all good. But if you were like, oh, I'm kind of rusty on this stuff, maybe you do the rest of this worksheet. That's up to you. I'm not going to collect this worksheet. It's there for your practice. You can always check the answer key for the rest of the problems. All right, so let's talk about how to graph results of our experiments. Okay, so what we have right here are data tables. They're just a way to present real clean, neat appearance of the results you got from a lab. And okay, so they talk about our independent variable. So independent variable is always on the left-hand side. And remember our independent variable, that is what we are testing. And our dependent variable is always on the right-hand side of these data tables. And again, our dependent variable, that is what we are measuring or observing. So in this first set of data, time is our independent variable. So we're going to put that on our x-axis. And the distance that these rockets travel is our independent variable, which will be put on the y-axis. So down here, I have sort of like a checklist for all the things you need to do to make sure you have a perfect graph. Well, first off, we want to put a descriptive title at the top. Let's not get too fancy here. Titles should be kind of boring. I don't even make a sentence when I do these. I keep it simple. So our independent variable for this is time. Our dependent is distance. So I came up with something like this. Rockets, distance traveled per second. There you go. Nothing fancy there. So I sort of use this as a checklist. So the moment I get my descriptive title at the top, I'm like, boom, check, good there. Labels on each axis. So the independent variable goes on the x, and then the dependent variable goes on the y. Okay, and I want to make sure I include units for those. So my x-axis goes my independent. I got time. I'm putting in parentheses after it seconds, so you know it's not minutes or hours. And then on my y, I got my dependent. So I got my distance, meters. Put a little m in parentheses for meters. Sweet, we're killing it. Mr. Pilcher, this is so thrilling. Just as cool as you setting stuff on fire. So boom, labels on the axis, done. Proper units next to those labels, done. Okay, so scaling. This is probably the most important part of graphing. Okay, the whole point of a graph is to make it easy to understand what happens, to have a nice visual. So knowing that, you need to make sure that your graph is scaled properly. So I say make sure you scale to 2/3 or 3/4 of the graph paper. In other words, make sure your graph, you have the whole thing that it fits on there, but at the same time you want to take up most of the space. Okay, and a key tip here, you do not have to start at 0. You do not have to start at 0. Lots of times you will, you don't have to. A lot of folks feel married to the idea of starting at 0. So what I ask myself is, what are the lowest and highest points I need to know? So I look at my data here. Okay, time starts at 0, okay, and it goes to 36 seconds. So, all right, I want my scale to be a teeny bit bigger than that. What's a clean number that's a little bit bigger than 36? Why don't I just call it an even 40, because that's an easy number to work with, multiple of 10. Then my rockets, they both start at 0. One goes all the way up to 98. The other one goes up to 89. So again, I'm thinking, okay, I need a number a little bit bigger than that so I can fit them all on there. But I want that number to be clean, easy to work with. So 100 is a little bit bigger than both of those, and it's going to be easy to work with. Okay, so I come over here and I create my scales. So my x-axis, I want to go up to about 40 seconds. So I want to make sure these 40 seconds are spread evenly across this axis here. So if I go ahead and count through this, I'll find that there are 20 lines going across. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 20. So knowing that, I want to divide that evenly. So lots of times I'll find the halfway point, be like, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so that's halfway. And then I'll sort of split it up into halves again. So half of 10 is 1, 2, 3, 4, 5. Over here, 1, 5. There we go. So that's about halfway there. Okay, so now I have it split up into 4 even sections, and it's 40 seconds. So here's where it's nice that I have a nice clean number to work with. So if I go ahead and just split these up evenly, I can just be like 10, 20, 30, 40. Nice. Okay, over here, this graph going up, you also have 20 lines going up. So I went ahead and did this ahead of time. So I split it up into 10 even sections. Okay, so at the top I know I have 100. I know the bottom down here is going to be 0. And so I split these all up evenly and I went by tens. So that's how I did it. So this way I know that my graph, my graph is big enough, my scale I should say is big enough to include all my data, but at the same time my data should take up most of the graph. You want it to take up most of the graph. Okay, so scaling, we're gravy. Yeah, make sure all your data points are visible. And add a key if needed when you have more than one set of data, which in this case we do. We have 2 rockets, so we're going to have to add a legend. So, all right, I'm going to make rocket 1 red. I'm going to make rocket 2 green. Okay, so this is my legend right here to indicate, hey, which line is which. So I'll go ahead and fill in my points for red. So I had 1 point at about 2 seconds and is close to 10 meters, and so on and so forth. So these red dots here, these are my data points, and then I just kind of toss the line on top of them to sort of clean it up, sort of smooth things over. Did the same with my green rocket number 2 right there. So I'm going back to my checklist, making sure I'm not forgetting anything. Data points are clearly visible. You got it. Key if needed. You got it. And you should be able to talk to me about what kind of relationship these guys have. You don't have to write down the graph lots of times, but you want to understand what kind of relationship they have. So we have 2 things. A direct relationship is basically the independent and dependent variables do the same thing. So if the independent variable is going up, then you'd see the dependent variable go up with it. That's when you have a direct relationship. So they're both going up together, or you'll see them both go down together. If they're doing the same, if they're going the same direction, that's called a direct relationship. An indirect relationship is when they do the opposite. So let's say the independent variable is getting bigger, but the dependent variable is getting smaller. Okay, so while one goes up, the other is going down, and vice versa. Okay, so let's see what's happening here on this first graph. Well, as the x-axis goes up, as we go to the right, we notice that the y-axis is also going up. See that? So our data is going up together. So we would say that this is a, oh, hello. We would say that this is a direct relationship because our independent and dependent variables are both going up together. Okay, so there's more practice for you here. Use the same checklist here. I'm going to go ahead and go through it very quickly. So you may have to pause the videos at video times. So I make sure I get a nice descriptive title at the top. I went with mass versus time. How does the mass change over time? And then I got my variables on my axes labeled. Okay, so the time is in minutes now. The mass is in grams. Then I went and I scaled. So if I'm looking at this data, okay, the time goes close to 100, or it goes all the way up to 90, so I'll probably just call it an even 100. And then here's an important point. The mass in grams, the highest point is just below 20, but its lowest point is only 16.8. So we do not, okay, don't forget this rule right here. You do not have to start at 0. This is going to be big on this one, okay? Otherwise, your scale is going to be all goofed up. So for my x-axis, I'll probably just go with the typical 0 to 100. And I split that across. There we go. So 100 would be right around here. And I labeled my every 15 minutes because that's the data that I collected. But with my mass, I have a point that's as low as 16 point something and one that goes up to 19. But that's my range. So I'm just going to make my range an even 16 up to 20. So my top number up here would be 20. And you'll notice I did not use 0 at the bottom of this axis. Okay? If I put 0 at the bottom of this axis, that means 16 would be up here and I'd have like a pretty straight line graph that doesn't take up much space. That's not what we're looking for. So if you go from 16 to 20, you'll get your graph to take up most of the space right here, and it'll look something like this. The last question I want to consider is what type of relationship do we have? Do we have a direct relationship where both the variables go up and down together? Or do we have an indirect where one goes up while the other goes down? Well, we'll notice as time goes up, mass is going down. So they're doing the opposite thing, unlike the last graph. So this would be a good example of an indirect relationship. Indirect relationship. And again, that means that the dependent and independent variables are doing the opposite thing. One is going up while the other is going down. In this case, our independent time is going up as our dependent mass is going down. So that's that for graphing. Your graph does not need to look exactly like mine, but it needs to look like mine in the sense that the graph takes up most of the page. A lot of you guys, if you accidentally use 0 down here instead of 16, your graph is going to look something like this, where it only takes up like this much of the page. That's not good scaling, and that would cost you points on a quiz type situation. But with my graph, you see, oops, there we go. With my graph, you see that it takes up most of the page. It doesn't take up literally all of the page. There's a little bit of empty space up here, but it takes up most of it, and that's good scaling. So you need to be able to draw a graph, but you also need to be able to interpret a graph. So that's where this worksheet comes into play, practice interpreting data. This is great practice here. You can find the answer key on Schoology. I would just go through, do a couple problems without looking at the key, then double check with the key. And if you're having issues, maybe do more practice problems, or you can feel free to contact me. And yeah, that's going to be it for today's lecture. Let me know if you have any questions.